taken from Dr. Mitesh Kapra and Dr. Swabha's presentations on recurrent neural network. Okay, so what I have thought for today's my plan to take this session is like we'll start with the introductory background which is required to understand recurrent neural network, which I'm sure everyone is already knowing, but I'll quickly go through the important points in 6 minutes about like what is a logistic regression, what is a neuron, and how we train a standard multi-layer neural network, and then we'll see how that network can be optimized and make recurrent connections to make so that it can deal with different kind of problem like sequential learning problem. And then we'll see the architecture of the recurrent neural network, and then we go into the depth of how we can create an RNA architecture, and then how we can train the RNN model. Okay, so that will be the time like outline of this presentation. Will in the end we'll also see the problems of RNN, and then the solution of the RNN, the problems of the solution of problem of the RNN will discuss in the next session tomorrow in LSTM. Okay, so let's start with the logistic regression. Everyone of us already know that this is a simple logistic regression architecture in which we have weights and connections. Like for example, we have three inputs in this x1, x2, x3, and so on. We have inputs, and with each input we have associated weights. And the first step, what we do is we do the weighted sum and pass it to the activation function. And activation function is for non-linearity, and then we get the output. And in the output, we compare it with the actual output, and then based on the error which we find using the cross entropy loss function, and then we back propagate and then update the weights. So that is the process which we follow. Okay, so I'm sure everyone is knowing about it. Just placing some activation function, sigmoid, 10H, rectified linear unit. Okay, so that is key ingredient of the neural network, because it helps in learning the non-linear activation and non-linearity in the function in the. Okay, so based on the combining multiple neurons, which somehow works like independent logistic regression models, which if we combine them into layers, we can say it as a multi-layer neural network. In this example, which you can see on the screen, is like in the first layer, which is an input, we pass it the input x1, x2, x3, and so on. And also the bias associated with each of the connections. Then the hidden layer, H1, H2, S3, all these are nodes in the hidden layer, and then output layer. Okay, so output layer for this example, we have a Y1, Y2, and Y. So that basically the total number of classes in the output layer. Okay, and W is basically can be represented as all the weights which is in between the input layer and the hidden layer, and U can be treated as a matrix which have all the weights in between hidden layer and the output layer. Okay, and if we represent this in equation, we can write output layer as y is equal to sigma. If we take activation function, it's a sigmoid function, so which we can write as sigmoid w dot x plus b. Okay, so this is very important how we convert the network into an equation, because we will be heavily use it in understanding and representing recurrent neural network. Okay, so for this example, if we have, let's say, x inputs and output y, so w can be like represented in a vector with all the weights in w. For this example, we have one vector, and x1, x2, and all these inputs are basically your inputs, okay, weights and inputs. So by doing the dot product of this, we can get the weighted sum, and then we can add the bias and pass it to the activation function, sigmoid activation function, and that will be our output. And similarly, if we have multiple classes in the output layer, we should use softmax function so that it will provide the probabilities that the class which should be predicted should have highest probability. Okay, so apart from that, everything is similar to the single one layer neural network. Okay. So see here, which is very important when we'll try to represent the equations in recurrent neural network is like when we have x1, x2, and so on to as an input values, and h1, h2, and so on is as hidden nodes. So how we can represent hidden layer h? So h can be represented as a dot product of weight matrix, and x is your input matrix input vector. Okay, so this is the notation which we can use to represent the hidden layer. Okay, so G is an activation function which can be ReLU, NH, or whatever. So whatever with the activation function which we want, we can take it as a activation function here. Okay, so H can be represented as G of W dot X plus B. And Y is similarly, Y is like basically U dot H or U multiply H. Okay, and now because this is predicting binary outcome, that is why I've taken sigmoid. If it will be predicting multiple classes, we should have used softmax function in the output layer. Okay, softmax. So this equation, I'm sure it is clear to everyone because it is, this will be using it in this way of representing the neural network. Will use it in recurrent neural network. Okay. Now we have already seen that language modeling with the help of probabilistic method. Then we have seen similar way of using the language modeling concept in learning the representation of the words in word2vec. And now we can also use recurrent neural network for language modeling. Okay, so recurrent neural network provides a quite good learning for learning the language models in predicting the words. Okay, so I'll show you some example, and then we'll. So the neural network can be used, feed forward neural network can be used for language modeling, and then we'll see also that recurrent neural network. Okay. So for a simple feed forward neural network for predicting the next word, like solving the language modeling problem. So given that, given the previous words, WT minus 1, WT minus 2, and so on, and we want to predict the next word. And we can do this with the help of, combining the concept of neural network and word embeddings, which we have learned in the previous sessions. And what we do is like we have a sliding window, which is basically takes the context of the words, and then based on the words which are now represented as an embedding, now all the words with their embedding we can feed to the network and then try to predict the next word. Okay. So now this is like language modeling, and as we have already seen that this is a self-supervised method, and XI is basically capturing all the context words based on the window size which we have decided, and the YT is the location or the word which we want to predict. So all these vectors are represented with one hot vector, which we already seen that word will be represented with the vector in which the size will be the vocab size of the vector will be the size of the vocab size, and it will have what value 1 at the position in which that particular word appears in the vocab list. Okay. So this is quite obvious that this embedding is already having semantic information into it. So it is it should work better than the methods which we have already seen. So this is an architecture of language language modeling using the neural network. Okay. So see here in the input values, like for example, for, all, and the, we are taking three as in context words, and one word, the next word we want to predict. So the window size of the sliding window becomes 4, including the target word. Okay, so now in the first phase, first layer, in the input layer, what we'll do is we'll represent the each word with their embeddings. For this example, the word for is appearing at 35 position in the vector, so it will be like 35, and the embedding of this word is taken. Okay, and then similarly for all and the, so the input layer basically have embeddings of all the words which we want to take in the context. And then we have a hidden layer, and then we have an output layer. Because this is an multi-class problem, so we have softmax at the output layer, and each node at the output layer try to predict the next word based on all these three words. Okay, so this is the way that we can use a neural network, feed-forward neural network, for language modeling. Okay, and uh, in each feature in this embedding vector is connected to all the hidden units. Like for example, if we have embedding dimension to be 100, so all these 100 nodes will be connected to all the hidden units. So 100 will be connected, 100 nodes will be connected to H1, 100 nodes will be connected to H2, and so on. So that way you have D by 3D, DH by 3D number of neurons connections. Okay, and you can also observe that the dimensions which you have in output layer is V. Okay, that is the vocab size, and it will predict the value next word, and the probability value will be high, and it will be in the one hot encoded method. So for example, if let's say the fish is predicted, it will have highest value, and since it is a one hot vector, we know that this word which has been predicted is fish. Next word is fish. Okay, so this is another representation, simplified representation of this. So given these context words, we feed it to convert it to the embedding, which becomes our input layer. Then we have your hidden layer, and then this is your output layer, which is trying to predict the best word, the best possible next word. So based on the highest probability represented with the softmax, so fish is the word which has been predicted next. Okay, so this is like just to give you an idea that how we can use language modeling. We can solve a language modeling problem with the neural network. Okay, that is also known as feed forward neural language model. Okay, so if you will notice here that this is a feed forward in which all the connections are fully connected with each layer, like input layer and hidden layer, all the nodes will be fully connected, and all the nodes between hidden layer and output layer will also be fully connected. And when we have like deep neural networks, like if we have multiple hidden layers and large number of neurons, so it becomes like a problem because of the overfitting. And that is why when we want to develop a deep neural network, by just concatenating or adding multiple layers in between, it gives a lot of problems related to the overfitting mostly. So we need to change like in the architecture itself, so that we can avoid the overfitting, and at the same time we can also learn a lot of in-depth information from the text. Okay, so that is the standard neural network. And now we'll see that this neural network is not suitable for special kind of problems like a sequential learning problem. And then we'll see that how we can use recurrent connections in the standard neural network to make it more suitable for mostly sequential learning problems. Okay, so what do you mean by sequential modeling and sequential learning? So that means when we have input values, which is for each sample, the input is given to the network and we just predict the output, but we don't bother about the previous inputs. So a lot of situations will can see in real time that when we want to predict something based on the input, we also want to see what has been in the past. So all those kind of problems in which we also want to take the inputs, information from the past or inputs, we should go for the sequential learning problems, and we can use a recurrent neural network to solve those kind of problems. Okay, so we'll take some examples here to understand that what are the problems in a standard multi-layer neural network and convolutional neural network. I'm sure you will be learning convolutional neural network in today's latest session, but you can for now you just see that the problems of convolutional network in the context of sequential learning problem is quite similar. Like both of these kind of networks take a fixed size input. So whenever we have a feed forward on multi-layer neural network, convolutional neural network, the main problem is the input size is always a fixed value. So if we give train a neural network, we have to fix the number of neurons in the input layer. And similarly, in the convolutional neural network, we have to fix the image size if we are using convolutional neural network for images. And if we are using it for text problem, text classification problem, we have to limit, that the length of the sentence. So if you are getting different length sentences, so in that case you have to use padding. And in that by using the padding, we have to make that network to input to the network to be of the same size. And padding is basically gives a lot of noisy information to the network, which is not desirable. So that is why it is important to understand what are the available architectures which we can use for one problem is like input size. If we want to have input size to be variable, and one is obviously that we want that the network to learn the past information also in addition to the current information. Okay, so for example, in CNN, if we feed a fixed size input of 32 by 32 images to the network for image classification, so for example here, if we give an image of apple to the network, it will predict apple. But for next example, let's say we give a car to the network, it will just predict the car based on only the current input. It will not bother about what has been the previous inputs. Okay, so that is like a network is independent of the previous or future inputs, and which we have already seen in the word to vec also, that we have to have a fixed embedding dimensions of words. Okay, so one problem which we could see so far in existing feed forward and convolutional neural networks is that the input size is fixed. And what if we want to have inputs of variable length? In that cases, recurrent neural network come in. And also that the input, the network should predict the output based on the current input and also based on the previous inputs to the network. So in that case also, all the existing models will not work well. Okay, so let's first see some of the application which we can see this kind of sequential data, and then how we'll then see how recurrent neural network can take all these things into consideration. So one of the popular application is in speech recognition, in which speech data comes into sequences, and at any moment of time we want to predict speech, we should take into the previous sequences into consideration. And machine translation, if you want to take a machine translation, given a sentence you want to convert into different languages, so we would be happy to take all the words in a sequence one by one and then process, and then produce the translation. So it works quite better instead of taking whole sentence into the one network and then try to predict a complete translation, because the input size also may change for the text. Okay. So that in that kind of situation, recurrent neural network and its variants are very useful. Another application is language modeling, which we have seen. The recurrent neural network, if you want to predict the next word given the previous words, let's say for here, for example, recurrent neural, if we give to the network, we can predict the network. And if we give recurrent neural network base, so it should predict language. So when we want to predict the next word, it is quite good that we should take all the words in the sequence, so that the context and the information is fed in a sequential manner, instead of directly giving all the context words, which we have seen. But yes, the recurrent neural network will give better like a better performance on language modeling task as compared to the standard neural network, which we have seen just now, that for the language modeling. Because in that case also we have to fix the input size. So for example, we have fixed the input to be 3. So that would be better if we take multiple input size in the context also. And sentiment classification also, if we want to predict that sentiment of this sentence, there is nothing to like in this movie. So given this sentence, we can directly do it with the standard neural network and convolutional network, but it would be better if we process each word in a sequence and then try to predict what is the outcome. In that sense, it will take a lot of like all the previous informations in predicting the outcome, and also there will not be problem of variable length input, because in the real-time situations, that sentences which we which we see in real world are of different lengths. Okay. Video activity analysis also, if we have a video, so each frame of the video can be taken as a sequence, and then based on that we can see if there is some activity also. Okay, so in that also recurrent neural network and other its variants are very useful architecture. Okay, so now we will see step by step that what are the different benefits which we want in sequential learning, and which are provided by the recurrent neural network. The first, which we have already discussed, is that input and output can be of different length in different examples. Okay. And you can see this example in which, as I mentioned, that if sentences are of different lengths, in that case, we have to do the padding to give it to a network. And these paddings provides a lot of undesirable or noisy information to the network, which is not good. Okay, so that is why we want to have that network which can take a variable length as an input. And in recurrent neural network, we'll see that we can take care of this problem, in which the sequences can be one by one can be given to the network without worrying about the length of the input. Okay. So this is another example where we are trying to predict the part of speech. Okay, this is part of speech problem, in which given the sentence, we want to predict the part of speech of each of the word in the network. Now, another problem with the standard neural network is like the information which we learn is like not taking word order, for example, in sentences, and also not taking the temporal and sequential information. So for example, consider the first sentence. So market falls into beer territory. Okay, so now based on this, we want to predict if it is trading or marketing, otherwise not. Okay. So main thing is, if you'll observe here, so second sentence, Kill sentence is made of just by changing the order of the words. So for standard neural networks or convolutional neural network, both will work same. There is no difference because when feed forward neural network or convolutional neural network, they will not see the orders or the sequence of the inputs. They will just take both the sentences same, which is not good. Okay, so that is why this sequence of or the orders of the words in a sentence is very important when we process it for different applications. So we can use these, but this word ordering information is lost. And that is why recurrent neural network is somehow desirable, more desirable, considering this, that attribute of learning the word order of or sequential pattern in the sentences and the words. Okay. So we'll see today that how we can process all the words. First we'll process market, then we'll process the false, then into, then beer, then territory. And whenever we'll process any given word, we'll also see the previous words, which was not there in the feed forward neural network or convolutional neural network. And that way it also take care of the syntactic and semantic information in the network. Okay. And here beer, false, and all. So all because of the change in the order, we could correctly predict the outcome using the recurrent neural network, but it will not be possible with feed forward or convolutional neural network. So basically, direction on information flows, that is very important attribute of recurrent neural network, which take care of the sequence and the direction of flow of the information. Okay, so in RNN, it performs well when the input data is interdependent in the sequential panel. So if the data is coming in the sequence, and at any moment of time, the output is just not depending upon the current input, but also depending upon the previous inputs. In those kind of situations and input data, the recurrent network should be experimented. Okay. There is a relation between previous inputs and the current input. And convolutional network feed forward networks are if your output and output is self dependent, it is not depending on the previous things, and it will not remember the previous input. So just given a fixed length input, it will try to predict the output. Okay, so if that is the nature of the problem, then you can try a convolutional neural network or feed forward neural network. Okay, so now I think we have discussed the what is the recurrent neural network situation, sequential learning situation, and where we would be happy to use recurrent neural network. Okay, so what now we'll talk about is how we can deal with the sequential learning problem, and how we can decide, okay, this is a sequential learning problem. Okay, so in sequential learning problems, what we need to care about is, first, the network should be able to handle variable length sequences. Variable length sequences, it means that the input size should not be fixed. We should not will not be using the padding or anything to make a fixed length input. Okay, and the second is track long term dependencies. It means whenever you want to predict the outcome based on the current input, but what we want here is we should also look the previous inputs, and based on the current input and the previous inputs, we should be the network should be that predict the outcome. So that we have to see if it is present in the architect network or not. Okay, in that case, we'll say this is a sequential network. Third is maintaining the. Okay, so there is some question in the chat. I don't know how I can. So there is a question as for words in the vocab, we can create one hot encoded vector, but how vector representation can be done in case of padding? What will be the embedded vector in that case? So embedding in that case, generally we take a zero values. So it will not impact anything, like all the connections will not be activated. So in that case, we generally take a zero value. Okay. And third is to maintain the information about the order, like the sequence is all very important. So that will take care that the inputs, all the inputs in the sequential manner should be processed in the same sequence. And then fourth one is share parameter across the sequences, which we'll talk about in detail that why sharing of the parameters is important and across the sequences. And then we'll see its importance as well as that how it helps in learning a different word order, as well as it reduces the parameters, which was like problem in converting in creating multiple layers of hidden layers in multi-layer neural network, in which we could see that overfitting problem. But here we'll see that we'll be using like sharing of the parameters concept, which will reduce the number of parameters. So, sequential learning problem, we have to solve these kind of sequential learning problems. We have recurrent neural network, which tries to solve sequential learning problems. Okay. Now, when we want to create a recurrent neural network, first thing that we'll always see in our network is that it should account for dependence between inputs. It should account for variable number of inputs and make sure that the function executed at each timestamp is the same. This is very important because uh, what we want is we want that all the see here, we want that the parameters should be shared across the sequence. And in our network, if we'll have, you know, that each timestamp, if we'll have different function to be executed, will not be able to share the parameters between different timestamps, and will not be able to forward the information from one timestamp to the another timestamp. And we'll see and talk this in detail later on also. Okay, so now we start with uh, uh, with some applications, like let's say we start with this character prediction problem. Okay, so in this, let's say we have one character as an input, and this is a connection, hidden layer connection. What we want here is successive inputs are no longer independent. While predicting the next word, will based on the previous character, we would be happy to predict the next character. So for example, I now given a word D, I predict a next character as E, and then given a next character E, I would like to predict the next word E, which is predicted E. But when I give this input E, and if I do not consider the previous information D, so in that case, the next character which is predicted as E, it could have been any other character also. And what we want is like when we give a new character as an input to the network, it should predict the next character based on all, not only this current input, but also based on the previous input. Okay, so that is what we want here. Okay, so when I have predicted E, so next when I give a new character, new input as E, so when we predict this P, it should also, while this predicting character P, it should also see the previous characters. Then only it will be able to correctly predict the next character P. If it will not see the previous inputs, this network will not be able to, correctly predict the next character P. Yeah. So next, after P, let's say we give P and now it detects like stop. So this becomes a complete word by giving by character prediction thing. Okay, so second thing which we can observe here is that the length of the input is not fixed. So for example, here we have only 4 characters. If we would have like 5 or 7 or 8, like in machine we have like 7 characters. So we just have to give one character by one character, and it will automatically stop when it will predict that character is stop. Okay, so there is no requirement of that having fixed length input. So the first thing with this architecture, we can ensure that, okay, given any character, we are based on the previous input we are predicting, and also there is no fixed length input in this architecture, and rest of the conditions will also see again in okay. So third is each network is performing the same task. The third condition in which given this input in this timestamp t1, if I give one vector, that is vector for D character, and one this is a hidden layer in which we process the input layer, and then it is predicting the character, next character. So each timestamp, if you observe, each timestamp we are doing the same thing, that given a character, predicting the character, given a character, predicting the character. Okay, so on. And all we have seen that first, there is no limitation on the input. There is no fixed length input. Second, we want that when we predict a character P, so it is also depending upon the previous connections. So for that, how we can do, we'll see. But just to clear here is that these boxes is just like a standard multi-layer neural network. So just before going ahead, let's try to go into these details, like what is there in the orange, blue, and green boxes. So you see these as connections. So for example, if I just draw this one here, so it will look like this. So let's say this is my input, and let's say in my input, let's say the D is represented with the dimension 4, and 4 is basically the embedding size. And now it is just like hidden nodes. So this blue box has number of hidden nodes. Here, let's say we have three hidden nodes. So 3 neurons in the hidden layer. Okay, and then in the output will have total number of classes, means total number of possible characters which we can predict in the output. So let's say that is have let's say 20 or 30 characters. Okay, so this will have 30 neurons here. Okay, so given this architecture, it is just like a feed forward neural network, which is like fully connected neural network, in which all these connections will be connected to each other fully. Okay, and just for the sake of simplicity, we just write this complete network like this. So this is just a box, this input box, this is your hidden layer box, hidden node, and this is your output box. So when we give one character with the help of embeddings, we have this hidden layer, which is represented this and this. So this one connection is basically showing that it is fully connected. So if we have 30 nodes here, it will be fully connected with all the nodes in the hidden layer. Okay. So this is just like a standard neural network. If we do not connect them in between, it will be similar to this. So each network is basically given a character, predicting the character, given a character, predicting character, and so on. Okay. And we stop automatically when the network predicts that it should stop. There is no need for having, multiple no need of using padding or anything else. Okay. And each input, as we have discussed, this each input is given at one time stamp. So time stamp one, when I give D, it will predict E. And if time stamp two, let's say we have input as E, now we are predicting next character E, and so on. Now, next thing, before trying to understand that how we take care of these connections, let's take another example in which we have that sequential learning problem. Yes, this is a part of speech tagging example, and in which, let's say, we take a sentence, man is a social animal. And what we want to do is we want to predict the part of speech of each word. Okay. So given these words, first we'll check that what are the attributes or the characteristics which we want to take care. First thing is that all the functions should do the same task. So in this network, you can see that uh, given a word, we are predicting part of speech. So part of speech, total part of speech is fixed, let's say 13, 14, okay, noun, verb, article, and so on. And input is a word. So in each time stamp, we are doing the same thing. And second is all the words are in a sequence, and it can be of a different length. So whenever we stop giving input to the network, it will just stop. And at any moment of time, let's say this is t is equal to 4. If we give social, it is predicting adjective, and it will also, we have to see that how this prediction is also based on the current input social, but also based on the previous words. Okay. And it is this sequential information or previous information is very important, because when you know that, okay, this word predicted is adjective, you are very sure that after adjective, the next word is most likely a noun. There will be very less chances that the next prediction, which is a noun after the object adjective, is like a verb or article. It is very unlikely that in a grammatically correct sentence, after the adjective, we see a verb or article. Okay. So that kind of that is why it is quite important that for this problem, also part of speech tagging problem, when we want to predict the part of speech, it should also see the previous sequences. So based on the previous outcome, let's say after the verb, it is, sorry, after the noun, based on the grammar, we can have a lot of information predicting the next word to be a verb. Okay. So we see that current input, current output is depending upon the current input as well as previous inputs. Size of the input is not fixed, because sentences could have arbitrary number of words. And notice that here we are interested in producing an output at each time stamp also. We'll see in next example that sometimes we are not interested in all the outputs of each time stamps. Okay. And also that at all the time stamps, we are doing the same task. Okay. So given a word, we are just predicting one of the part of space tag. Now, this is an example in which we can use the same recurrent neural network architecture, but we are not bothered about the output of each timestamp. Okay, so now let's see if this example follow all the conditions of sequential modeling. Okay, so let's say we have a sentence, the movie was boring and long, and you can see here that uh, the length of the sentence is not fixed. It can be of any length. Whenever we want to predict the sentence will be completed, it will be predicted at positive and negative. Okay, so given the sentence, we want to predict if it is conveying any positive sentiment or negative sentiment. Okay? And the second thing is each timestamp, we are doing the same thing. Given a word, we want to predict if it is a positive, not positive. Given a word, we are predicting if it is positive and not positive, and so on. The only difference is in each previous timestamps, we are just not taking care of it. We are ignoring it, but each timestamp we are doing the same task. Okay. And whenever we predict, it will also see the inputs of the previous words in a sequence. Okay. Now we'll try to understand that what are the functions being executed at each timestamp. Okay. So this is t is equal to 1, this is t is equal to 2, and we are doing the same task. But what is the task which I already discussed with you, that this is just like a standard multi-layer neural network, and the representation of this is we can easily write the equation for this. We have also seen in the starting of the lecture that hidden layer here represented as. So Si can be represented as the sigmoid function if we are using sigmoid activation function in the hidden layer, which is nothing but U is the matrix of weight matrix between all the connections for all the connection between input and hidden layer. So U is having weights of all the connections between input layer and output layer, and Yi is basically the output, which is basically the output is your output function based on like for this example, we have multiple classes. So we have softmax as an output. So based on what is the problem, what we want to do or predict in the output, we can have output function, and that can also be written as v dot x si plus c. C is a bias, and v is basically your weight matrix in which we have weights of all the connection between hidden layer and the output layer. Okay. So now see here that at each timestamp, we are having the same function. So at t is equal to 1, we have the same function, that is Si sigma u xi plus b. And if we make the t is equal to 2, now you can observe that when time t is equal to 2, we are using the same function. Okay, so same weights are there, like here V is there, here is also V. It means the connections, weights between these in hidden layer and output layer are same. So when I'm giving T at x1 at time T is equal to 1, the things will be processed. And when I'm giving x2 at T is equal to 2, I'm feeding it to the same network. Okay, so that is why it is important that each timestamp we do the same function, we execute the same function, and all these weights are being shared. Why it is important? Because if we will not do this, if t is equal to 1 and t is equal to 2, if this will be u1 and let's say this is your u2, the weights will be different, let's say. So in that case, we'll not be able to, consider the previous sequences. And when we pass the information from t is equal to 1 to t2, that can only be passed through these weights. Okay, so we'll see different possibilities of passing this information from t is equal to 1 to t is equal to 2, which is like we can directly pass from here, or we can pass from here, or we can pass the information from here. But in that case, we'll if we'll not have same parameters to be shared in different timestamps, information will not be that network will not be like having previous information, because that way we'll have different functions and different orders. Okay, that is why it is important that we share the weights between different timestamps and we execute the same function. Okay. And that is why just making multiple copies of the same network n times, basically depending upon the inputs, we can execute them in a sequence. And that is why there is no requirement of fixed length input. Okay. So now the next point is very important, which we are talking already, that what we want is the information from the previous inputs should also be considered when I give a current input to the network and predicting the output. So how we can take care of the dependence between different inputs? So we have already seen the other conditions, like there is no need of variable length inputs, like fixed length input, and we can have variable length input. At each timestamp we are doing or executing the same function. Okay. And uh, and what we want now is how to understand how we can take care or can incorporate the information of previous information when predicting the current timestamp. Okay. So let's see uh, some infeasible way of doing it, like why we cannot directly connect these. Let's say this is at time is equal to t is equal to timestamp t is equal to 1. We give x1 to the network and predict y1. And at timestamp 2, when we have x2, we can directly give x1 and x2 to the network, to the second network. And likewise, if we have a timestamp t is equal to 3, we can directly we could have given x1, x2, and x3 directly to this network, and it could predict the y3 and so on. But it is not desirable solution, because it will violate one condition which we have thought so far, is that at each timestamp, the function that we want to execute should be same, and the parameters between different timestamps should be shared between all the networks. Okay, so parameters and should be shared, and what we want is at each timestamp, the function that we want to execute should be same. But in this case, if we go with this architecture, it is not same. Why it is not same? Because for t is equal to 1, the function that we are executing here is only depending upon x1. But if we go like this, so in that case we'll also have to have u1 and u2 connections. So all these weights will be extra weights. Now u1, u2, u3. And similarly here you will have connections like u1, u2, and u4. And as will increase in the timestamp, these connections will also increase, and it will not be possible for the network that the condition of executing the same function at all the timestamps. Okay. So the main problem here is that the function which we are executing is different. Okay. Now this is a function of x1. This is a function of x1, x2, and this is a function of x1, x2, and x3, and so on. If we have let's say 10 timestamps, then that function will become a function of 10 variables. And that is why we have two other options. Sorry. So that is why we cannot directly like connect like this. So it will be very complicated also. But the main problem is at each time, like for this, it will have three inputs for x1, x2, and x3. Here it will have two inputs. Here it will have three inputs. Okay. And what we want is at each time, it should only execute the same function. First thing. Second option is like if we connect this hidden node with the next node, which is mostly we have seen so far also in all the materials if you have seen before also. And another option is we could have connected from here. That is also possible, but this is the best way of doing it because the hidden node representation is basically a timestamp, sorry, state representation, all the information which has been learned so far. So just focus here. So this representation, which is giving output here and there. So this representation is basically the state of the network of all the information received in the network so far, and which you can like observe here is that we are giving input x4 to the network here, and all the information is passing through the hidden layer. Okay, so when you are giving x2, so this representation will encode the information from the current input and the previous inputs, and that will be given to the output and the next node. And when we receive here the information from previous two informations and we give x3 as an input, it will encode and process and convert, will give the encoded information, which will have the information from x3, x2, and x1. Okay. So whenever we process this, it will also take the information from previous states, but obviously it is like how much information of the previous states is being used here. So that we'll see that as we go back in the network, depth in the back, in the back in the network, so the contribution of x1 slightly become less as compared to x3 when we'll be processing x4, just because when we go back in the network, we have to have compute the weights using the gradient of these weight matrices, and we'll see later in the lecture also that as we go depth in the network, the contribution or the weights becomes smaller and the contribution becomes smaller. So that is a problem of network RNN that we'll talk about it later on. So, but here what I want to explain is that 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 at any moment of time, the hidden representation is basically encoding the information of all the previous inputs, and that is being used for the current so for the next unit. Okay, and in the next unit will take care of the previous information and the current information. So for example, here it will take all the information which is basically stored in this, and the current information which is being processed from xn, it will now process and give the output. So uh, in recurrent neural network, first thing that is important, and we have to see that if it is taking care of variable length input, so that is like not a problem in this case because we process each sequence in each time stamp, and then there is no fixed length input. Also we can have any input, and the prediction of the output at any time stamp, it is also taking care of the previous inputs with the help of these recurrent connections. Okay, and we can write this equation now at any moment of time stamp t, let's say this. So now there are connection between input layer and hidden layer. We can write it like this: u x xi, because it xi is your timestamp, and all the weights connected between the hidden layer and the output layer, which is basically W and S of T minus 1. So this will give all the information from the previous inputs. So when we want to predict at any time storm, we are using the current input and also using the information from the previous inputs. So that way, this equation now is a recurrent neural network architecture in which we can see that the output of hidden node at any moment of time is taking care of the current input and also previous inputs with the help of this st minus 1. Okay, and now when we predict output, it will be like a v s of I and plus c bias. We can also write this equation like this, which is compact representation. It means the same, which shows like a yi. The output is basically a function of xi. Xi is the input, and si minus 1 means the previous inputs. Okay, and the weight matrices are like W, which is the connections and the weights between the hidden to hidden nodes. That will also be like that fully connected neural network. So let's say we have 4 nodes here. So we'll also have 4 nodes here. So these connection will be 4 cross 4 matrix. So we have 3 weight matrices and biases. Okay, so if you want to, compute or calculate total number of parameters in the network, so that we can uh, compute like this. So let's say the input dimension is n dimension vector, that is mostly the embedding dimension, and number of nodes in the hidden layer is, let's say, d. So we'll have like in U will have this is your N, this is your D. So N cross D will be the number of parameters in U, and similarly in V, let's say K is total number of classes in the output. So in V will have D cross K matrix, and W will be D cross D. Okay, so these will be the dimensions and the number of parameters in this network, and biases, obviously. Okay, so that is about the internals of recurrent neural network, how recurrent neural network is built, and how it processes the information. And now we'll see different possible architectures. Some of them we are already seeing, but we are just complete discussing once again that what are the different possible architectures of recurrent neural network. First, we have seen in character prediction and part of speech tagging that one-to-one network. Second is your many-to-one, many-to-one, in which we just ignore the outputs of previous like timestamps. And many-to-many in music generation also, and machine translation will have many-to-many connections. So this is another representation of recurrent neural network, since you already know that this is a recurrent neural network in which we at any time stamp t, we have xt as input, v matrix is given to this node, which is basically information from previous nodes, and this is current information, and that way we just go this like this. But the compact representation of the same network, because all these weights are shared, so we can just write it like this, which is very common way of representing the recurrent neural network, which at any moment of time t, the output is depending upon the current input and also based on the previous inputs. So this recurrent connection is basically taking care of your previous inputs. Now I'm showing you another example for better understanding and visualization. Okay, so this is in sequence of words, which is basically represented with an embedding. For this example, embedding size is 4. and which just taken one hot encoded representation. Okay, so we can take any representation, but this is, for example, let's say 4 dimension is the input sequence, and then these WXH is basically weight matrix between connections between input and hidden layer. And in hidden layer, we have three nodes. Okay, so all these connection means this is basically 4 x 3. So this all the connections are fully connected. Okay, and then this is the output layer. So this output layer we have 3 classes for this example. Okay, so this has 3 nodes. We have softmax, which will compute the probability. So, and you will observe that this at each time stamp we are giving the same input, okay, and same output is being predicted. So function being executed at each time stamp is same. There is no limitation on the input layer, and the information is also passed to the next layer when we are to predict the current predict the output. It will also it will be based on the current input and previous inputs. So all these conditions are being fulfilled with this recurrent neural network. Okay, and uh, you can also see that when we pass from the first time this time the hidden representation is being updated, and when we go here last, it will based on previous information and the current information, it will predict the current output. So when it will predict that the location, it will see, okay, what was the previous part of speech words. Okay, this is another representation for the character prediction. Okay, so I'm sure now it is very clear that this is input layer, then hidden layer. Here we have taken, let's say, 10H as an activation function, and which is nothing but WHH, which is a weight matrix between the input and the hidden layer. And this is hidden connections between hidden to hidden, and this is connections between the input layer, okay, and then bias. And similarly, we take the output. And each time we are predicting the character as an output. Okay, so this is an architecture which where we can use a recurrent neural network for language modeling. So for language modeling, we have seen with probabilistic method, then we have used like a similar type of concept for word to vec, and then we have seen in the morning that we can use standard feed forward neural network for predicting the next word. Similarly, now we can see the architecture that we can use for predicting the next word using the recurrent neural network. So in this architecture, I'm sure everyone of you is now clear that what is the architecture. In this architecture, you can see that given the words, now the student studied the. So at any time, a moment of time, at any moment of time when we want to predict, it will not only see the current input, but it will also see the previous inputs. Okay, so uh, the hidden representation, or let's say the output at hidden node at any moment of time, h of t, is basically the activation function, and weight matrix between the hidden to hidden layer and the weight matrix between the hidden to input layer. Okay, and output layer we have softmax, and then we have, so it will predict the output at every moment. So next word will be predicted based on all the previous inputs. Okay, the student studied the, given these 4 words, now we can predict the probability of the next word. But now it is also using it is like using the recurrent neural network. Earlier we, in the language probabilistic language model, we computed or estimated with this with the help of that counting the frequencies and all, which was not that good. But here we are using embedding for the representation of the words, and then processing a sequence which is more semantically rich and syntactically important and good representation. Now we Now, uh, now we'll see how we train the network, recurrent neural network. In standard neural network, multi-layer neural network, we use backpropagation process, which you already know that given a sequence of in the network, we give the input and we compute the output. At the output layer, we compute the loss, and then based on the loss, we just backpropagate the loss, and using any let's say optimization algorithm like gradient descent or Adam, we just update the weights, and iteratively this process continues till the loss is minimized. So that way we used to do in standard neural network. But let's see how we can do training and train the model in recurrent neural network. Okay. So we'll also use cross entropy. Basically, we'll use the cross entropy function at each time stamp. So you just see this architecture. So at any moment for each time stamp t, let's say this is t is equal to 1. And when we give input and we compute the loss. And the loss we compute very similar to the to what we have done in the standard neural network. We just compute L1 for t is equal to 1 and L2 for t is equal to 2 and so on. So what we do is we compute the loss at each time stamp and L1 and then L2 and 3 L4. And what we do is basically we average all the losses of all the timestamps, and then we backpropagate uh, this loss with the from the network. So basically the will go from like this. So at any moment of time, let's say I'm at t is equal to 2. So when I will backpropagate the loss, it will be like going to the in the back directions. And when we backpropagate it, I'm not going into the details of the mathematics of this at the moment because of the limitation of the time also. But I'm sure it is like if you have seen that chain rule in which we have to backpropagate the loss from one layer to another. So if you will see, when we backpropagate this, so we have to like for example, let's say I want to find out the losses here. So what will happen is it will multiply all the weight matrices n number of times, and that is very problematic in the recurrent neural network, because when you multiply a lot of matrices, so somehow multiplying small values n number of times, let's say 0.1, if you will multiply 0.1 10 times, so the value becomes very small. So what happens in recurrent neural network is like when we go deeper in the network, so what happens is like the earlier weights becomes very small because of multiplication of small values in the matrices. Okay, and that is called a vanishing gradient problem, and that is why we'll talk about this also in when we'll talk about LSTM, that how it impacts learning in text problems, text classification problems. It will not take care of the inputs in the of the starting sentences, for example. Okay, so vanishing gradient problem means that weights are now in the starting layers becomes very small, and they are not contributing in prediction at any moment of time. And to just see the some of the previous inputs, it will not go to the depth of the network, and that is because of the weights becomes very small. And similarly, yeah, here we have discussed also that when we compute this, so this will become gradients of different layers, and it will somehow multiply matrices multiple times, which will create very small values. And that is why it will not learn. And exploding gradient problem is somehow very similar, but the problem here is when you have, let's say, slightly more value at, let's say, 1.1 for one weight value, and if you'll multiply value which is more than one and multiple times, that gradient becomes very big, and it will not help in training the model. Okay, so the recurrent neural network has mostly two major problems: vanishing gradient problem and exploding gradient problem, which is which hurts the performance of recurrent neural network. No, okay. Recurrent neural network in which the main problem is that the information which is in the starting of the sentence, which will not be used for predicting the next sequence. So see this example, like when she tried to print her tickets, she found that the printer was out of order. She went to the stationery store to buy. After installing the toner into the printer, she finally printed her. Now, if we want to predict this word, we will not be able to take the context, which is quite far from that particular timestamp, which is like tickets. So this is a problem of recurrent neural network, which is because of the vanishing gradient problem, in which when we go back into the network, the weights are basically stopped updating because it becomes very small, and that learning becomes stop for initial or early layers, early timestamps. And now just recapping what are the advantages of RNN. It can process any input length. The model size doesn't increase for longer input, so there is no need of fixed length input. Computation for each timestamp can use information from previous steps, but not much in recurrent neural network. But we'll see different other variants of recurrent neural network in which we'll be able to use longer that timestamps information. And weights are shared across the timestamp, which is a condition that not neural network should see the previous inputs. So one more thing is like sharing is also important, because otherwise we'll not be able to see the information. If we'll have these different weights, will not be able to have that the information passed to the next layers also. Recurrent neural network disadvantages is like its computations is very slow, and it is difficult to access information from many steps back because of the vanishing gradient problem. Okay, just all the things we discussed so far, just written in this. So now, given the time, I would like to have some time for the discussions. Thank you. There are some questions in the chat I could not see.